Hi everybody, sorry about that. I had an issue that came up that I needed to resolve. Let me wind this down here. Alright. Welcome back to Chem 121. Oh, just a second. Sorry. I'm talking to another faculty member about something. There we go. Okay. Alright, today we are going to start Chapter 3. Relevant announcements and things that are due and upcoming. So last call for lab worksheet number 1 is tonight. Last night, everybody had questions for me. That is good. I am happy to answer questions. Tonight, I will be mostly unavailable. So if you are planning on getting a question to me and asking, like, hey, how do I do this at the last minute, I'm not going to be available until like 10 p.m. If even that. So, beware. Like, I will be very limited availability tonight and also Friday. So just rule of thumb for these things when you're working on them. If you have questions, get those questions in as early as possible, just in case. Quiz number 2 should be posted. If it's not, I will fix that. The due date for quiz number 2 is April the 26th. That is a Tuesday. Yeah, that's where we're at. So we're going to do Chapter 3 today. Chapter 3 is pretty short. Just like with Chapter 2, how there was a section at the end that we don't do. Chapter 3, I actually exclude a bunch of stuff. Mostly because I feel like it is too technical and beyond the scope of this class. Even though it is included in the textbook. And that's these sections, not the laser pointer. There we go. That's these... why did that not work? There we go. That's these sections right here. So everything about electron arrangement. We'll mention what that means later. There is a soft deadline for Labs 2, but the soft deadline was yesterday. So today is last call. So this is the 24-hour period after the deadline. So the hard deadline is tonight at 6 p.m. There should be an email that automatically goes out that says, hey, last call, turn this in or don't get credit. So that is tonight. So make sure that you have that in tonight or it doesn't get accepted. Which would obviously be no good if you've been working on it all week. So, all right, we're going to actually do chemistry now. No more math for a little while. I know how much you guys love math, right? So we're going to move on to conceptual stuff, such as, what the heck is an atom? Here's an atom. This is a picture of an atom drawn as a sort of cartoon, but this diagram is not 100% accurate. It is just a model. Now, if you are familiar with any sort of like science, the symbol that is used for the atom looks something like this, where there's like a little blob in the center, and then there's stuff going around the outside. So maybe something like this, where here's like a little circle, and then you have like a ring going around like this, and then maybe another one like that. We've all seen this symbol before, right? It is a caricature of the atom, and for the most part, it is a decent representation, but it's not to scale by any means. If it was to scale, you'll see what will happen here in a second, or as it turns out, you won't. All right. So in the center of the atom, we have this very dense part called the nucleus. The nucleus is unbelievably dense. Like, holy shit dense. If you had a teaspoon full of nuclei from atoms, it would weigh over 1 billion tons. You could fit all the mass of all people on Earth into a teaspoon if you just condensed everybody down into the same density of the nucleus. In the nucleus are these particles, protons and neutrons. And they are compacted in the center, and they just kind of hang out there. On the outside here is the electron cloud. The electron cloud is basically anything that is not the nucleus. It is the empty region that surrounds the center of this atom. You can think of it as like its airspace. Now, in that airspace are electrons. Electrons buzz around like very, very angry bees. and they move extremely fast, and they move extremely chaotically. On this diagram, I have shown the electrons moving around on what looks like constrained rings, similar to how the planets orbit the sun. Now, for planets, that model works really well, but for electrons, it doesn't. And we're going to talk about that reason on the next slide here, so we'll get to that in just a second. Now, the other thing to mention is that the diameter of the nucleus relative to the diameter of the electron cloud is actually a ratio of the nucleus would be 1 and the electron cloud would be 52,800. So if this diagram on your monitor shows the nucleus with a width of 1 inch, then the edge of the electron cloud where the electrons would reach out to would actually be some 0.8 miles away. So in reality, what you would have is you'd have this giant electron cloud. So we'll just say that this is my electron cloud, this yellow, because that's the highlighter I had selected. And then the nucleus inside, if this was to scale, and I go like this, boop, that's too big. That's too big by like an order of 10. So it's extremely tiny relative to everything else, which implies that most of the atom is just totally void. There's nothing in there. It's all empty, except for the teeny tiny dense part of mass at the end, at the center. Sorry. Now, that's interesting because we obviously are not empty voids ourselves, right? Or at least we don't think we are, it turns out. If you are sitting on a chair right now, which I don't know why you would be standing watching lecture, maybe you're exercising, you're at a standing desk or something, or maybe you're like me and your knees hurt. I'm not actually standing, I'm just stretching at the desk. Isometric exercise or something, I don't know. You'll notice that you don't pass through your seat, right? If you were completely empty space and so was your seat, shouldn't you just pass through? Kind of like you were a ghost or something? And the answer is, well, no, you don't do that at all. You can impact any surface. So, like, I'm going to hit my table here with my palm. I have no idea if you could hear that. Let me... Yeah, that spiked on my mic. Okay. And my hand doesn't pass through the table. So, there's something interesting going on here for sure. If we are completely empty space, like 99.9999%, because atoms are just that empty in general, why do we not fall through stuff? And the answer to that has to do with this very important property called charge. Charge is one of the fundamental properties of the universe. We have protons, which are in the center here, and electrons, which are on the outside, and they have opposite charges. You might know of charge from things like electricity. Electricity is an application of charge. If we move charge through a circuit, we can power things by using electrons, right? This is how you are seeing this video on a screen, is a circuit is conducting electrons through it, and we're using charge to power your device. Atoms naturally have charge. And the particles inside the atom, the proton and the electron, have opposite charges. And what we notice about charges is that the following effects occur. If you have the same charge as another object, you repel it. Like charges repel. However, if you have opposite charges, you will be attracted to that other thing. So this can happen when you do like static electricity with a balloon on your head. When you rub the balloon on your hair, you are rubbing electrons off of your hair, and so there is a lack of electrons. There's more positives than there are negatives. All the electrons are on the balloon, and so when you bring the balloon to your hair, it sort of sticks there, right? Or you can put it on the wall and it will stick there too. So we can do things with charge, and we can observe these effects. Now, back to the question I asked you earlier, why do we not just pass through matter? Well, let's go over here, and we'll draw a picture. All right, so here is the table. And then here is somebody's hand. Yeah, it looks terrible, I realize, but there we go. That looks a little better, I guess. Okay. And you were going to put your hand onto the table. Now, if I were to zoom in really closely to where you were contacting the table, what I would find is that the atoms of your hand and the atoms of the table so these are all atoms. What is going on here is that the outside of each atom is an electron cloud. And I apologize that my pen is freaking out here. I didn't reboot my computer, and I should have. On the outside of the electron cloud are electrons, right? So here's all sorts of negatives, and all sorts of negatives on these atoms over here, and so on and so forth, all over the place. What do electrons do to other electrons? Well, they're all negatively charged, so they repel. And so when you put your hand on the table, what you are actually feeling is a repulsion by electrons. This is going to drive me crazy every time I write the letter S. If I do it too fast, it's going to connect them. Because Photoshop... Ugh. So electrons repel each other, and the force that you feel from pushing on a table or standing on the ground pushing back against you, that is the force of repulsion by your electrons being repelled by whatever you're sitting on or are standing on or pushing against or whatever. So charge is a very practical thing for our everyday lives. Now, there's another particle in here called the neutron, and the neutron has a very specific purpose that we're not really going to talk about in this course because it goes beyond the scope of chemistry. This goes into nuclear physics. So, and oh my goodness, I have fixed this typo so many times. Hold on. Just a second. So, this says weak nuclear force. This is not the weak nuclear force. This is the strong nuclear force, and I don't know why that typo keeps coming back, so we're going to fix that real quick. There we go. So in your notes, it may say weak nuclear force. This is supposed to be strong nuclear force, but it's not beyond the scope of this class anyway. What the strong nuclear force is it is an attraction between neutrons and protons so that the nucleus sticks together, because in the nucleus, all the protons are hanging out, and all the positives would repel from each other if there was not some force holding them together. And the force that does that is the strong nuclear force. And that requires the presence of neutrons. So really, the point of neutrons being in the center of the atom is they are the nuclear glue that keeps the nucleus from falling apart. And that's really all you need to know. So those are our three component parts. Our subatomic particles that we're going to care about. Electron, proton, and neutron. The force? Yes. I was trying to do a Yoda voice, and then I sort of abandoned it there. Alright. Now for a given atom, an atom is always electrically neutral. So what I mean by that is that this word and this statement go together. An atom is electrically neutral. That means that the number of protons and electrons within an atom is the same. If it's not the same, It's not an atom. Now, the reason that this becomes important is because it is very easy to add or remove electrons. The nucleus is essentially untouchable. It is in the center, it is extremely dense. Doing a chemical reaction does nothing to the nucleus. It just hangs out. The electrons, however, are very tiny and they're very far away and they move around very quickly. And it's easy to just bonk them into things where they go flying. Whew. Goodbye, electrons. Turns out that all of chemistry is just that. How do we bonk electrons around and rearrange them so that we get new and interesting things? So by adding or removing electrons to an atom, it is no longer electrically neutral and it becomes this. This is called an ion. An ion has a different number of protons and electrons. All right, well, we're going to come back to ions a little bit later. But very important to keep those in mind because we're going to focus on those in Chapter 4 when we talk about ionic compounds. Excuse me, just drinking some water there. All right. So there's your homework practice for this section. Is literally just like a diagram. Look at the atom and label stuff. So, all right. So that's our blueprint of the atom. It's going to look something like this, just not as cartoonish, I guess. So now that we've seen the visual version, let's write out some symbolic stuff for it. The first thing that we're going to need to do is we're going to need, that's not at all what I wanted. So P table, why isn't this opening? There we go. Google was being obnoxious. We're going to need this link right here. And then I need to put this on the screen. I don't want the chat. I want this one. That's what I want. Boop. All right. This is P table. And we don't really need all the ads and stuff down there. I'm going to cover up the chat for a second here. P table is a very useful website that organizes a bunch of chemistry knowledge that we have compiled over the course of civilization. You're going to want to be using P table and have it handy for various applications in this class. What those applications are will become important as we get to them. For the first part, we're just going to be identifying parts of atoms and aligning that with features on the periodic table, and then talking about why we've categorized the periodic table how we did. So that's the entire focus of Chapter 3, is why is the periodic table how it is? And how does that correlate to our understanding of the atom? So have this handy. And what I want you to do is click on any element that you want to, and it will have its description appear up here. There is a link to Wikipedia that you can click on, and it'll actually pop up like what it looks like, what it's good for. And so you could do this for any element you want to. I'm not going to make you do like a sort of research project because whatever, right? But what's important here is that you'll notice that no matter which element you pick, at the very top left corner is a whole number. That number is called the atomic number. The atomic number is always written, no matter what periodic table you're looking at, as an integer, and it is somewhere along the top of the box for your given element. The atomic number, by definition, and we have created this system so that this is true, the number of atoms, or the number of protons within an atom, is the atomic number. So on the screen here, you can see that I highlighted 54 and in the box for Xe. So that atom, xenon, if you are a xenon atom, you have 54 protons. In fact, you must. If you had less than 54 protons, you would not be xenon. You'd be some other element. And if you had more, you would still be a different element. If you had 53, you'd be iodine. If you had 52, you're tellurium. If you had 50, you're tin, and so on. So every atom on the periodic table has a specific number of protons. Now, why did we do this? Why did we select this? It's because it is very difficult to change the number of protons. Therefore, we have accepted that, okay, if it's difficult to change this, that feels pretty constant. That way I can have an atom that isn't just changing its identity willy-nilly as I'm doing stuff with it. And in chemistry, that will never happen. In chemistry, atoms do not change identity because they do not change the number of protons. So hydrogen will not spontaneously turn into lithium or oxygen or what have you. Now, in things like fusion or fission or physics, that can happen because the nucleus is changing. But we're not going to talk about those until probably chapter 10. Which I don't think we will... Actually, it's chapter 11. We don't do radioactivity in this class, other than a lab assignment that I have you do. But anyway, that's going to be relevant to us. We need to remember that we can identify an atom with this facet, with this number that is written on the periodic table. We're going to assign the atomic number a variable, and that variable is Z. For Chem 121, this is really the only time that we use Z as a variable. In chemistry and other classes, though, we use Z as the atomic number quite often for other features of quantum mechanics and calculations that we can do. Here, you just got to remember, okay, Z atomic number. You're going to use it for one purpose, and you'll see it in a second. The next number that we're going to assign a variable to is A. A is called the mass number, and the mass number is the number of protons, just like the atomic number, but the number of neutrons is added to it. So if I had a nucleus, for example, and my nucleus had 31 protons and 36 neutrons. Here's what we would do. Protons are the atomic number, so Z would be 31. A would be the number of protons plus the number of neutrons. So A would be 67 for this nucleus that I have constructed. So be careful about this, because the temptation to just say, oh, A is neutrons, because I already did protons, right? And then you'll get the wrong answer if you do that. So be careful. A is protons plus neutrons. You need both. Z is just protons. All right. Now remember that if an atom is neutral, i.e., it is not an ion, then the number of protons and electrons will be the same, so Z would tell you the number of electrons as well for a neutral atom. That is also relevant, because what we're going to do in a second is we're going to start filling in these charts, and the charts are going to be, I have an atom with 31 electrons and it is silver. How many protons does it have and what's its charge? Like, that sort of stuff. And you'll be able to identify all this because you know what element it is by name or atomic number or whatever, and you can start looking up things on the periodic table, which you haven't closed yet, have you? It's still right there, yeah? We're going to need it, so just leave it open in a tab in Google. I don't care if you have 600 tabs, I do too. Welcome tab 601. Now, the next thing I want to mention real quick is that the mass number is unique. We're going to talk about what the mass number is used to calculate later on. So the mass number and the atomic mass are not the same. For instance, if I open... Oh, I'm going to sneeze. Sorry, hold on. Sorry, I had to quickly hit mute. For instance, if I open up the periodic table here, and I go and click on hydrogen, and you'll notice that at the bottom here of hydrogen, this is 1.008. That is not the mass number. That is called the atomic mass, and that is something related but different. mass numbers will always be whole numbers. Because, again, mass numbers are the number of protons plus number of neutrons. And these will be counted. The atomic mass is something else. We'll talk about that at the end of Chapter 3. All right, so let's put all this information together and make a symbol out of it. So here's what we're going to do. Right here, I have curly brackets E. What I'm going to do is I'm going to replace curly brackets E with some atomic symbol for an atom that I am being asked about. You do not need the curly brackets. You do not need the E. You replace the whole thing. Oh, thank you. Hopefully you didn't hear me sneeze. I thought I hit the mic, so. Once you have written the atomic symbol for your element that you are looking at, you're going to import the atomic number Z in front of this as a subscript. And so that looks like this. It's going to go at the bottom right before your atomic symbol. Then you're going to import the mass number as a superscript right in front of the element, so it looks like that. And then the last thing that you should do is celebrate, because you're done. So what you have done here is, so there's two names for this. There's complete chemical symbol notation. The other one is called isotopic notation, which you may hear me refer to that from time to time because other textbooks call things different things. And then this notation that I have right here, I just made up on my own. So this is, I call it ZAE notation, because it is shorter for me to typeset that into a table. Now you'll notice that I cannot put the Z directly under the A because Microsoft Word doesn't let me do that. What it should look like is this. And so when I type it, it's going to be typed out where they're offset like that. And they shouldn't be, but it's very difficult for me to typeset a subscript and a superscript in the same space. All right. So let's do an example here. I've got a carbon atom. And my carbon atom has 6 protons and 6 neutrons. What do I write in front of my carbon? So in the chat, write what Z is, write what A is for this specific atom. And I'll give you a minute to think about it. All right, I need just a moment because I need to check something. So I will be right back. Go ahead and type Z or A in here for this question. All right, sorry about that. I'm trying to debug something for a quiz, and I don't know what's going on. And e-learning is emailing me, and I want to get to them before they leave for the day. All right, so how would we write carbon with 6 protons and 6 neutrons? So if we go to the periodic table, let me make sure this is still pointed at this. Yeah, there we go. And I go to carbon. So you see that carbon has 6 protons right here. So that means that Z for carbon is 6. So we'll write that. So here we go. And then it also has 6 neutrons. So what I'm going to do is I'm going to add the protons and neutrons together. And so that's what I get for my mass number is A. A equals 12. All right. So what I want you to do now is I want you to construct symbols for each of these situations that I've made. So I've tried to like disguise this in a way without me just telling you what to put in there. You're going to have to use the periodic table. So again, here's your periodic table. Make sure you are using that. I'm going to give you a chlorine atom with 16 neutrons. I want you to write its isotopic notation symbol. I'm going to give you some atom with Z equals 25 and A equals 55, and so on and so forth. And then down at the bottom, I want you to tell me how many protons, neutrons, electrons for whatever specific thing each atom has. Remember that these are all neutral atoms. So no ions yet. Same number of protons as electrons in each atom. Okay? Go ahead and do this. I'll give you 4 or 5 minutes or so, and we'll go over the answers in just a bit. 1 or 2 more minutes, and we'll go over the answers and take a break. All right, let's go over the answers here. So I want to, let's do this. All right, and then I need to window capture the periodic table again. So let's see if I can. I'm going to just do this one. We're going to just put this over here on the calculator because we don't need it right now. But let's look at this first atom, chlorine. So I'm going to click on chlorine so that's on the screen. All right, I have an atom of chlorine with 16 neutrons. So it's chlorine, so the symbol for chlorine is Cl. Chlorine's atomic number is at the top of the box there. It's 17, so for Z, I'm going to write 17. Oh, I hate you right now, Photoshop. Don't know why it's Photoshop doing this. All right. Oh, you can't read this because I am hiding it behind the thing. There we go. All right. And then I have 16 neutrons. Remember, A is the mass number, so that's 17 protons plus 16 neutrons. And so we would write 33 right there, and there's your symbol. All right, for the next one, we'll just do this. Boop. So I've got Z equals 25. A equals 55. So I'll just write that in there. And now I got to write the symbol in. So the number on top of the periodic table, right here, I'm highlighting it in blue. This is number of protons on this guy right here that I'm moving around. The number on the top of your symbol is the mass number. So this is A, and this is Z. So be careful. Now I got to look at what element is element number 25 with 25 protons, and that's this. Boop, manganese. So I would write its symbol. And there you go. And then finally, same number of protons and neutrons, and A is 36. So what that means is that number of protons plus number of neutrons equals 36. And these are the same number, so I could call them X. 2x equals 36. I thought we weren't doing math anymore today, Wes. Well, you could use algebra for anything, right? So, if the number of protons and the number of neutrons is 18, Z must be 18. What element is 18? It is, boop, there we go, argon. All right. So there's the first three problems. We'll just clear that so I have more space. And then I will do this. We'll leave the homework practice on the screen there. There we go. How many protons does silicon... Oops, that's not my pen. How many protons does this have? Well, remember that Z is the number of protons. And that would be 14. I have to write extra slow today because my tablet must be just screwed up right now. All right. For the next one, how many neutrons does this potassium atom have? Well, if I look at this is A, which tells me the number of protons plus the number of neutrons. And if I want the number of neutrons out of there, well, I know the number of protons must be this, right? So the number of neutrons must be 39 minus this 19, or 20. Because 20 plus 19 makes 39, right? And then finally, how many electrons does sodium have with these numbers here? We know that Z is the number of protons, and for this case, it'd be 11. And then we also know that for a neutral atom, not atom, number of protons equals the number of electrons. And if I have 11 protons, I must have 11 electrons. And so there you go. All right. There's our solutions. And on the screen is the homework practice, problems 5 through 26. We're going to take a break for 10 minutes. So when we come back, we will finish up the rest of Chapter 3, because we're pretty much almost done at this point. All right. Oops. No, I do not want to update. All right. I will see you in 10 minutes. right, we are back. Hope everybody had a nice break. We're going to continue with Chapter 3. We're going to talk about isotopes. What is an isotope? An isotope is a description that is given to different atoms that have the same number of protons and electrons, but the number of neutrons contained within them may differ. So, for example, let me put a bunch of atoms on the screen with a bunch of different Z's and A's here. And you'll notice that all the Z's are the same. But you'll also notice that all of the A's here are different. Now, if A is the mass number, which is protons plus neutrons, what this means is that the number of neutrons is different for each of these. How many neutrons does each have? How would you figure that out? Type that in the chat. How many neutrons does each of these have? And then I'll show you an easy way to calculate it. There you go, 5, 6, and 7. Now, how did you get that number? I'm going to show you it this way. Hold on. So if Z is the number of protons plus the number of neutrons, not Z, I'm sorry. That's not what Z is. There we go. Thinking too far ahead. Z is the number of protons, and then A is the number of protons plus the number of neutrons. What would happen if I subtracted? Well, if I subtract this from itself, it goes away, right? So what I'd be left with is the number of neutrons. So if I just subtract the top number, A, minus the bottom number, Z, I will get the number of neutrons. So the number of neutrons for these must be, so number of neutrons, 10 minus 5 is 5, 11 minus 5 is 6, 12 minus 5 is 7. So if you need the number of neutrons and you have both A and Z, you could just subtract the two. All right. Now, anything that follows these rules, I cannot click on this damn thing. I don't know why it's not working. There we go. Let me tidy up here real quick. Anything that follows these rules, same Z, different A, is what we're going to call an isotope. Now, to call something isotopes, you need to have two things to be comparing against each other. The best analogy I can think of is that if you call two people twins, it's because they were born at the same time, right? Essentially. If you call two atoms isotopes, they have to follow this definition. Same Z, different A. So, in order to apply the label, you need to meet this qualification. So, the word isotope is actually a label. So there's our isotopes on the screen there for carbon that I've chosen. So they have the same Z, they have the same atomic number, but they have a different mass number, and that means that they differ in the number of neutrons, like we have said. Now, as far as isotopes are concerned, on Earth, every element, with some exceptions, has between 1 and up to 10 isotopes that are stable. These isotopes are what are known as naturally occurring. A naturally occurring isotope is present in some quantity in, say, the soil or the water or in the atmosphere. In other words, you could put it in a bottle and take it to the lab. Some isotopes, however, are known as synthetic. A synthetic isotope does not exist naturally, and the reason for that has to do with the stability of a particular arrangement of protons versus neutrons. Isotopes are still an atom, just a different classification. Isotopes are a label. So, two atoms can be isotopes if they meet this definition. Like, you wouldn't just point at any one atom and say, oh, it's an isotope. You have to compare it to something, right? Now, you could say carbon-12 is an isotope of carbon because you're comparing it to something, which is a generic carbon atom, and that's fine. But it doesn't make any sense to say this atom is an isotope and then not say anything else, because isotope of what? Because the whole point of isotopes is that we compare different things together to say that they are isotopes of something. Now, again, synthetic isotopes mean that they are not abundant in nature. You cannot find them by digging them up out of the ground. And there are various reasons for this. We talked about earlier that neutrons hold the nucleus together. If you try and create an atom and you put too few neutrons in its nucleus, it doesn't hold together. It falls apart. Likewise, if you have too many neutrons, the neutrons don't stick to the protons. And then they fall off too. So, depending on the arrangement of number of neutrons, there is kind of like a Goldilocks principle. There's a just right number of neutrons for a given number of protons. And so you can see on the periodic table, if you go digging around, how many different isotopes are available. So let me see if I can get this on P table. Let's see here. So for instance, if I want to look at isotopes of, say, oxygen, let me go to Wikipedia. Yeah, here we go. Okay. So if I go to Wikipedia and I look up on oxygen, let me make sure this is still pointed at that. Yeah, very good. And I look right here, it shows me the various isotopes of oxygen that are abundant. And so oxygen with a mass number of 16 is the most common. 99.76% of the oxygen you're breathing is oxygen with mass number 16. But there's also oxygen mass number 17 and oxygen mass number 18, and these are both stable. If I went to, say, tin has tons of isotopes. So let's see if we can get all those on there. There they are. The most common isotope of tin is tin with mass number 120. 118 is the next most common, and then all the other ones after that are just somewhat common. Tin 126 is very, 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 very rare and is actually unstable. So if you see something in one of these tables and you're like, oh, what the heck does this mean? This means it's radioactive. The nucleus is unstable, and so what it will do is it will fall apart in some way. All right. So we're going to explore radioactivity a little bit in a future lab. I have a lab about osmosis, dialysis, and then radioactivity. And it's one of those watch a bunch of videos labs. I wish there was more to it, but unfortunately, like, without doing in-person labs for this quarter, we're very limited in what we can cover. All right. So When in our discussion upcoming, we're only going to consider naturally occurring isotopes here. So anything that is synthetic that we have to make in order for it to exist, to work with, we're going to just pretend doesn't exist. And that's going to be relevant in this section because we're going to be looking at just scoops of random things out of the ground. So if I dig in the ground and I find, like, gold, for example, what isotopes of gold will I find? Well, I won't find any of the radioactive ones because they would have probably all decayed away. All I'm going to find are the stable ones. Now, because dealing with the mass of an individual atom is difficult... Oh, excuse me. Must be 2 p.m., huh? I don't know why I get super tired at 2, but it's just how I am. It's 1:37. It's close enough. All right. It is real obnoxious to deal with the masses of atoms in terms of grams because atoms are really, really small. A carbon-12 atom weighs less than 2 times 10 to the 23, or 2 times 10 to the minus 23 grams. That's real tiny. I don't want to deal with that number every time I want to consider how much things weigh. So what we're going to do is we're going to create a new unit, and that unit is called the atomic mass unit. The atomic mass unit is very straightforward for our purposes. One atomic mass unit is 1 proton or 1 neutron. Electrons are so tiny, we count them as 0 AMU, so we ignore them. So whatever an atom has for its mass number is going to be its mass in atomic mass units. Now, I'm hand-waving this a little bit because it turns out that the mass of a proton in AMU is like 1.00079 or something like that. But we don't care about those decimals for this class. If we just round to the nearest AMU and just count protons and neutrons, that's going to be good enough for us. Now, the definitions, I just noticed that there's no period here. The definition that we are using there, where 1 AMU is 1 proton or 1 neutron, is good enough for our purposes, but it's not good enough for science. And so let's talk about where this number comes from on the periodic table. So this number right here, you can see down at the bottom, 118.71. Where did we get this number? This is the atomic mass. But what does that mean? No atom weighs 0.71, right? Because you'd have to have fractional AMU. You can't have part of a proton or a neutron, can you? And you'll notice that if I go around the periodic table, almost all of these atoms land on some fraction, right? Very few, like these two, land almost exactly on a whole number. But they are definitely in the minority. So what's the deal here? What is this mass? What is the mass number's relationship to the atomic mass on the periodic table? How do I link those two things together? And here's how we do that. What we have done is we have said, okay, we're going to define some atom to have some mass. And so all of matter is based around this definition. The mass of a carbon-12 atom is exactly 12 AMU. And then we have tinkered with the definitions of grams and AMU and so on and so forth so that everything else syncs up. Because we said carbon-12 weighs exactly 12 AMU, we can then weigh any other atom and say, oh, it weighs half as much as carbon-12, so it must weigh half as much AMU. On the screen here, I have an example for boron-10. If I use a very precise device, I could find out, oh, boron-10 weighs this fraction of a carbon-12 atom. It's 83.442% of the mass of carbon-12. And when I multiply that number by 12, I get this. 10.013. Which is really, really close to the 10 that we would have predicted, right? So there is going to be some error in our calculations when we talk about AMU in this class. I say calculations, we're not going to do any calculations. But the point is that those extra decimal points can add up, especially when we do this next step, which is we're going to try and take averages of the isotopes that we observe. This mass is called the isotopic mass. What does this isotope of boron weigh? For our purposes, we would say, oh, it weighs 10. In reality, it weighs this. Close enough. To get the atomic mass, what we have to do is we have to consider all the different isotopes that are naturally occurring. And so, again, naturally occurring. Not every possible isotope, because boron 1 doesn't exist, right? You have to have 5 protons. You can't have less than 5 things in the nucleus. Likewise, boron 6 doesn't really exist because you'd only have 1 neutron. That one's probably not going to last very long. And you could make this argument for many of the different isotopes. There's only going to be a very narrow region of which they do exist. And which ones those are, you have to look up. There's no way to look at the periodic table and say, oh, which isotopes exist? We have to do the experiment. Do you always compare it to the carbon when we look for AMU? So this is the way that it is done when we actually weigh stuff. For our purposes, we're going to just look at the mass number. Now, when we determine the atomic mass, which is, again, this number on the periodic table, it didn't capture my window. Because I closed the window. That was silly of me. That's not... Where the heck did it go? Oh, I minimized it and I couldn't find it anymore because dumb. Where the heck? What on earth? Why? I'm literally looking at it. There. Okay. Sorry, OBS was being stupid. There's my periodic table. So, again, the mass number and the atomic mass, which I'm going to highlight right here, are different, but they are related. So how do I get the atomic mass of boron, which was right here? We'll click on boron. 10.81. How do I relate this to boron 10 that we have here? And we're going to show how that's done. I'm going to cover that example up real quick, but we're going to go back over here. I'm going to click on boron, and we're going to look at its isotopes. And you're going to see here that boron 10 is 20% of all boron. Boron 11 is 80% of all boron. And what I'm going to do is I'm going to do a calculation that tells us the weighted average. So let's go over here really quickly. And this is not a calculation that you are going to be responsible for. But I'm doing this just so you can see how this works. So 20% of all boron is boron 10. 80% of all boron is boron 11. And so what we're going to do is we're going to multiply the percentage times the mass. So 20%, or 0.20, times the mass of boron 10, plus 80% times the mass of boron 11. And when I type this in the calculator, 0.2 times 10 plus, parentheses, 0.8 times 11, I get 10.80. And this number is the atomic mass of boron. And if we go back to here and put this back on, you can see that for boron, look at that. We got real close to that number, right? So this number, the atomic mass that is shown on the screen here, is the average of all the isotopes and their masses and their abundance, okay? So that's where this number comes from. This number does not represent one individual atom. No atom weighs 10.8. But if I was grabbing a random assortment of boron atoms from a bin that contained all the boron in the universe, on average, it would weigh 10.8 AMU. Okay, so that's the whole reason we're talking about AMU at all, is just to get to this number, because we're going to use this number later in Chapter 6. But on the periodic table, the mass number is simply an average that represents the mass of just a random sample, because you're never going to take one atom, right? You're going to take a whole bunch of them, and you don't know which ones you're going to get. It's random. It'd be like if I had a bag full of dimes and quarters, and I said, reach into the bag and take out a handful of coins. On average, how much money would you get? You'd get some average between 10 cents and 25 cents, right? Based on how many dimes there were versus how many quarters, if you were just choosing randomly. In fact, we can do that example too, if that analogy helps you. So let's go back over here. So just like this was the atomic mass of B, let's assume that you have like a bag of money, and so like 25% of the coins are 10 cents, and 75% of the coins are 25 cents. So on average, if you grabbed a random handful, you'd get 25% times 10 cents plus 75% times 25 cents. I'm really angry at my PowerPoint right now, or Photoshop. This is driving me insane, this pen. And so on average, when you grabbed out of this bag, it would be like you grabbed a handful of coins that had this much value. So, but no coin actually has that value, right? So no single coin is worth this amount. But on average, they are. And with our atoms, it's the same principle. No single atom has the mass 10.80 AMU, but on average, they are. All right, so hopefully that analogy helped clarify what isotopes are and how we get this mass off of the periodic table. So one more example to talk about for this. If half your bromine weighs 79 AMU and half your bromine weighs 81 AMU, what would the atomic mass of bromine be on the periodic table if you just took a scoop at random? What would it be like all the atoms weighed on average? Type your answer in the chat, and then we'll talk about it. All right, so if half of it's 79 and half of it is 81, then the average is going to be right in the middle, right? And so the average mass would be 80 AMU. And so we can calculate that by doing this calculation. Half of 79 plus half of 81 is 80. That's how averages work. We've done averages in algebra class. And you can actually see on the periodic table that the mass of bromine is very close to 80. And if I click on bromine and we go to, hold on. We go to its isotopes, you can see that it's very roughly half and half, which is why the mass is very close to 80. All right. So here's some practice problems for you. Just to review what we've talked about for isotopes, that the mass on the periodic table, the atomic mass, does not tell you the mass of any individual atom. It tells you the average. Now, in general, whichever mass number is closest to the average is probably the most abundant one. So that's going to help you answer these questions. And then I want you to approximate the mass of this mystery atom X based on this information. 20% weighs 43, 80% weighs 44. I want you to tell me its atomic mass. So go ahead and answer these questions. We'll go over the answers in just a little bit. Two more minutes, we'll go over the answers. All right, let's go over the answers here. So for the first problem, you can do the same calculation that I did. And again, I'm not going to make you do this on a quiz or something. But just in case you were trying to figure out how these numbers were calculated for atomic masses. So we'd say 20% times 43 plus 80% times 44. So times 43 plus 0.8 times 44. And you get 43.8. Or in other words, it's 80% of the way between 43 and 44, right? That makes sense. Now for the next question here, if there's only two isotopes, and we're going to say that they're chlorine 35 and 36, it turns out they're not, but for this purpose of this question, this is the answer. Or these are the isotopes. Are there more chlorine atoms with mass number 35 or 36? Well, here is our average mass, right? Do you have to write the 0? No, you don't. I'm just writing it out because 2 decimal places is nice. This is the average mass, 35.453. What is that average closer to? 35 or 36? Well, it's closer to 35, right? So, there must be more chlorine 35 atoms than there are chlorine 36, because otherwise the average would be closer to 36 then. And then finally, what percentage of atoms have a mass of exactly this number? What percentage of atoms weigh exactly 35.453? And the answer is 0. None of them weigh that, remember? Here's what they weigh: 35 AMU and 36 AMU. How many of them weigh 35.453? None. No atoms weigh the average mass. The average is a number that we calculate. Remember the coins example. If I have a bag full of dimes and quarters, and you reach in and grab a handful of coins, it's like you grabbed coins with a value of 21.2 cents. But no coin is actually 21.2 cents. Just like if I reached into a bag and grabbed a handful of atoms, and on average they weigh 35.453, but none of them individually weigh that. All right. We have 2 more things to talk about before we continue. We're going to run out of time, unfortunately. So what I'm going to do is I'm going to talk about the periodic table for a little bit. We might do metals and nonmetals next time. After class today, I am going to put up the quiz for Chapter 3, so it'll be due next week. We're going to finish Chapter 3 on Tuesday, but it's only going to be like 1 question about metals. And if you want to read ahead and see what that is before taking the quiz, you'll be fine. I just don't want the quiz to be due week 5 for Chapter 3, so. All right. Let's watch a little video. Let's stop writing calculations on the screen because I need to reboot my my computer. I'm trying to pause this here. All right. So let's do that and this and that. All right. Can I get this on the screen? There we go. So, well, I'll just say it. Okay. So this is sodium. What we're going to do is we're going to put sodium metal in this little dish of water. Okay. And this is what happens when we add sodium metal. So this is elemental sodium. This is not sodium ion that we eat. This is elemental metal sodium in water. So that was interesting. Our sodium, when we put it in the water, it bursts into flames, right? There it is. Metal sodium is extremely reactive with water, which is kind of cool. So now what I'm going to do is I'm going to load up the next video here real quick. All right, so here's potassium in water. We'll put this on the screen here. Ready? Here we go. That was cool. We can look at this again. It's a little faster, it seems like, but it burns. This one's a pretty pink color. All right, let's do another one. I realize that that's actually not the potassium video I usually show, but that's okay. Okay. Here's rubidium in water. This one's real fast. So we gotta slow it down. And so what you're probably noticing is that, okay, Wes is showing us all of the elements that explode in water when we react them this way. And then here's our last element. This one is super fast. Blink and you'll miss it. Here we go. Done. Here it is in super slow-mo. So what we've learned from this is that certain elements will explode when you react them with water, and that's neat and all. But where did these elements come from? And let's find that on the periodic table here. Here we go. All right. Which elements did I select when I did that? So you'll notice I picked sodium. So here's sodium right here. And then I also picked potassium, which is right below it. And then I also picked rubidium, which is right below it. And then I also picked cesium, which is right below it. Look at which elements I picked. I picked all the elements in the same column. That's strange, right? In fact, there's a reason that I chose those elements. Because I knew they would all do the same reaction. And the reason they all did the same reaction is because they are all in the same column on the periodic table. We have constructed this periodic table in such a way that if a reaction happens for certain elements, we put them in the same column to reflect that. So for instance, all of the elements in group 1A, if you put them in water, they will burn. If you put elements in group 2A in water, they fizz and are not as reactive. They're very, very, very weakly reactive, relatively speaking. If I put elements from group 17 in the presence of metals, they react violently. They corrode the metal very quickly. And so on and so forth. I can do a bunch of different experiments, and all of the substances in the same column will react similarly. And so this is the basis of the periodic table. The periodic table was constructed in such a way to reflect that any elements within the same column will react the same or similar way under a given condition. Is it flammable? Does it react with water? Does it react with chlorine? Does it react with heat? Does it combust in the presence of oxygen? All of these are different experiments, and for each column on the periodic table, you can say yes, no, or maybe, or whatever. Another example, for our elements on the very far right on the periodic table here, in this last column, these are the noble gases, and the noble gases, like all nobility, sit on their asses and do fuck all, right? These gases do nothing. They don't react. They're totally inert. And that's a very strange coincidence. Why do we have these elements that don't do any chemistry at all? Well, whatever the reason is, we're going to stick them all in the last column. And that's the basis for the periodic table. And this guy realized that. This is Dmitry Mendeleev. Dmitry Mendeleev constructed the periodic table in the late 1800s so that we could categorize all of these different reaction types or patterns that we observe and throw it on a table so we don't have to memorize this stuff. So you don't have to memorize that it's lithium and sodium and potassium and rubidium and cesium that react with water violently. Like, that's so much to commit to memory when there's so many different reaction types out there. So the periodic table is set up for this reason, and because of that, it's even possible to use it to predict the presence of elements that had not been discovered at the time. So in Dmitry Mendeleev's time, they didn't know about elements like gallium or germanium or something like that. But the elements around it were known, so they could make predictions. And that's really cool. Here's a picture of our periodic table. When we come back on Tuesday next week, we're going to talk about groups and periods, and then we'll talk about the metal, non-metal line, and then we'll finish. That'll be the end of Chapter 3. Somebody asked me, are we doing the last two sections? So this is the last slide right here, is slide 25. So nothing past slide 26 is done. So that's like 40 slides. We're skipping all these 40 slides. We're not talking about electron configurations in this class. I could spend an entire class period on it, and it's totally worthless to you. So we're not going to do it. So let me put my marker back where we were. So we were here. I am going to put the quiz for Chapter 3 up because we have like 3 slides left for this chapter. There's very little left. And you could just read about groups and periods if you really want to take the quiz this weekend. So just to keep us on track here. All right. I do want to thank everybody for coming out to the lecture. I apologize for all the issues with my tablet. I'm going to hope that rebooting fixes it. Otherwise, I have a long weekend of reinstalling drivers ahead of me. Grumble, grumble. So let's see here. Lab worksheet number 1 is due tonight. The assignment closes, and once it's closed, you cannot turn it in. Make sure you get that in. Quiz number 2 is due Tuesday next week. Quiz number 3 will be due Thursday next week. And we'll talk about lab number 2 next week at some point. Okay, that's all I got. Have a wonderful weekend. Thanks for coming to the lecture. Get those assignments in, and we'll see you on Tuesday. Take care.